In the name of Allah, who is the most gracious and beneficent. My name is Nida Fatima, and I am the student of BS Chemistry in the University of Management and Technology. Today, I am going to present polyoxymethylene, which is submitted to Dr. Hammad Majeed. This is the basic structure of polyoxymethylene. We start our topic with the basic introduction. Polyoxymethylene is also known as acetal or polyacetal. It is a high performance engineering thermoplastic having notable properties as it has high stiffness, low friction, excellent dimensional stability, and good chemical resistance. It is also known by some later terms like polyacetal, acetyl resin, polytrioxin, polyformaldehyde, and paraformaldehyde. These are really short-chain polymer. As we know that polyoxymethylene is a plastic and this plastic is solid under some trade names like capital, Chalcone, Hostaform and Ultraform 2. The last three names Chalcone, Hostaform and Ultraform 2 are the copolymers. Copolymer is the version of polyoxymethylene. Now we study the development of polyoxymethylene. Polyoxymethylene is discovered in 1923 by a German chemist named Hermann Staudinger. He conducted extensive researches on polymers and the concept of macromolecules. His work laid the foundation for the development of polyacetal resins. Later, he received the Nobel Prize in Chemistry in 1953 for his hard work. Here are some uses of polyoxymethylene. Polyoxymethylene is commonly used in precision parts due to its ability to maintain tight tolerances and resist wear and tear. Because it is good for making precise parts, as it can keep everything fitting together perfectly, it does not easily get damaged from rubbing or regular use. So it is great for things that need to be very accurate and last for a long time. Polyoxymethylene is widely employed in various industries, including automotive, electronics, consumer goods, where its combination of mechanical strength and versatility makes it a valuable material for manufacturing components like bushings, gears, and connectors. Here is the chemical formula and molecular structure of polyoxymethylene. The molecular structure of polyoxymethylene is characterized by a chain repeating CH2O units. This gives rise to a linear polymer chain with oxygen atoms linking the carbon and hydrogen atoms. The basic structure can be represented as CH2ON, where N represents the number of repeating units, indicating the polymerization of formaldehyde molecules. Now we discuss some properties of acetyl resin. Polyoxymethylene resins demonstrate well-balanced properties ranging from mechanical to physical and flammability performance. The key properties of resins include excellent mechanical properties over a temperature range up to 140 degrees Celsius down to minus 40 degrees Celsius. It has high tensile strength, rigidity, and short-term toughness, low tendency to creep as compared to nylon, and long-term fatigue, which is not susceptible to environmental stress cracking. High degree of crystallinity and excellent dimensional stability. It has high gloss surface, excellent wear resistance, good resistance to organic solvents and chemicals at room temperature. It has low smoke emission, low coefficient of friction, and low moisture absorption. Now we discuss the production of polyoxymethylene. Different manufacturing processes are used to produce the homopolymer and the copolymer versions of polyoxymethylene. Homopolymer. First, we study the production of homopolymer. In order to make the polyoxymethylene homopolymer, we must generate anhydrous formaldehyde. Now we react anhydrous formaldehyde with an alcohol to create a hemiformal. Then the dehydration of hemiformal mixture by extraction or vacuum distillation process. So the water is extracted and then by heating the hemiformal we release formaldehyde. This formaldehyde is then polymerized by anionic catalysis and the resulting polymer stabilized by reaction with acetic anhydride. The example of homopolymer is DuPont's Delrin. DuPont Toluene is used in manufacturing precision parts for industries such as consumer electronics, healthcare, and industrial equipment. Now study the production of copolymer. In order to make polyoxymethylene copolymer, formaldehyde is generally converted to trioxane. Trioxane, specifically 1,3,5-trioxane, which is also known as trioxane. This is done by acid catalysis. The acid catalysis are sulfuric acid or acidic ion exchange reactions, which are followed by purification of trioxane by distillation or extraction to remove water and other active hydrogen containing impurities. Typical examples are hostoform from Celanese and ultraform from BAS. Here is the comparison between homopolymer and copolymer. Acetal copolymer is easier to process, having wider processing window, while the acetal homopolymer is available in several viscosity ranges. Acetal copolymer releases less gas and odor, while acetal homopolymer has high tensile strength. Acetal copolymers include heavy metal-free colors like cadmium and lead, which are safer for workers and environment, while unfilled homopolymer is stiffer and stronger. Acetal copolymer have faster molding cycle while the acetal homopolymer have shorter molding cycles. The molding cycle basically consists of several steps like clamping, injection, cooling, dwelling, mold opening, ejection, and mold closing. The time which is taken to complete these steps is known as molding cycle. Acetyl copolymer works under reacts under ultraviolet light exposure, while acetyl homopolymer allows thinner and lighter part designs. Acetyl copolymer is stable in alkaline environment, while acetyl homopolymer provide better mechanical properties. Availability and price. Polyoxymethylene is available in many colors like black, white, but it's not available in transparent. It's also available as plates up to 3 meter by 1.25 meter in thickness from 0.5 millimeter to 130 millimeter, and it is also available as round bars from diameter 5 millimeter to 200 millimeter. Its retail price in November 2023 in Netherlands is 19 to 27 euro per dm cube. Now we study the processing techniques for polyoxymethylene. Polyacetal resins are split in small particles. They can be molded into different shapes by applying heat and pressure. They can be processed by ejection molding, extrusion, compression molding, rational casting, or blow molding. Injection molding or extrusion are the most commonly used methods for polyoxymethylene processing. Polyoxymethylene resins must be processed in the temperature range about 190 to 230 degrees Celsius. Now we discuss the conditions for injection molding. Melt temperature. Homopolymer resins 180 to 230 degrees Celsius and the copolymer resins should be 190 to 210 degrees Celsius. Temperature molding is about 150 to 150 degrees Celsius. While using higher molding temperatures for precision molding, which is used to reduce the post molding shrinkage. Injection pressure should be about 70 to 120 millipascal and the injection speed is about medium to high. Now we discuss the extrusion processing conditions. Extrusion is used to remove semi-furnished parts such as sheets, rods, pipe, filaments, and profile sections. They are further machined using traditional methods such as turning, milling, drilling, etc. to form finished parts. The melting temperature should be about 180 to 230 degrees Celsius, while the screw speed is about 33 to 42, and the die temperature is about 175 to 230 degrees Celsius. Here are some advantages and disadvantages of polyoxymethylene. First, we study the advantages of polyoxymethylene and later on the disadvantages. Advantages. Polyoxymethylene has several advantages like it has high stiffness and strength as studied earlier. Polyoxymethylene exhibits excellent stiffness and strength, which makes it a suitable material for applications where these properties are very important. It has low friction characteristics, which make it a popular choice for application which are involved like in sliding or rotating parts like gears and bearings. It is chemical resistance. As we know that polyoxymethylene is resistant to a variety of chemicals, including solvents and fuels, which enhance its durability in different environments. Dimensional stability. Polyoxymethylene maintain its shape and dimensional stability even in varying temperature and humidity conditions, which ensure its consistent performance. Good wear resistance. Polyoxymethylene has good wear resistance, which make it suitable for application where components experience friction and abrasion. Low water absorption. Polyoxymethylene has low water absorption, contributing to its stability in humid conditions and maintaining its mechanical properties. Ease of machining. Polyoxymethylene is easy to machine, allowing for the creation for intricate parts with high precision and tight tolerances. Electrical insulation. It exhibits good electrical insulating properties, which make it suitable for electrical components and insulating applications. Versatility. Polyoxymethylene is versatile and find applications in various industries, which include automotive, consumer goods, and industrial manufacturing, among others. Now we discuss the disadvantages of polyoxymethylene. Polyoxymethylene is also known as acetal or polyacetal and is a versatile engineering thermoplastic, but it does have some disadvantages like high cost. Polyoxymethylene is more expensive as compared to other engineering plastics, which may reduce its use in cost sensitive applications. Next is susceptibility to ultraviolet radiation. Polyoxymethylene is sensitive to prolonged exposure to ultraviolet radiation, which can lead to degradation and the loss of mechanical properties. This makes it less suitable for outdoor applications without proper ultraviolet stabilization. Flammability. Polyoxymethylene is flammable and may burn in the presence of an open flame. Flame retardants are often added to minimize this, but, but it is still considered in certain applications. Limited chemical resistance. While polyoxymethylene is resistant to many chemicals, it may not be suitable for applications where exposure to certain harsh chemical is frequent. It can degrade in the presence of strong acids or bases. Creep resistance. Polyoxymethylene has lower creep resistance as compared to some other engineering plastic. Creep is the tendency of a material to deform over time under constant load, and in applications where minimum deformation is critical, this can be a disadvantage. Hydrolysis sensitivity. Polyoxymethylene is susceptible to hydrolysis under certain conditions, which mean it can degrade when exposed to water at elevated temperatures over extended period. This can impact its performance in humid or wet environments. Now we discuss grades of PM. The different grades options of PM resins are reinforced grades, high impact grades, grades with slipwear properties, ultraviolet stabilized grades, and nanocomposites. Reinforced grades. These grades show high tensile strength or rigidity. These properties depend on the type and the amount of polymer reinforcement. Glass fibers, carbon fibers, or glass spheres reinforced PM grades are available. High impact toughened grades. Blending polyoxymethylene resins with rubber, TPU, and other polymers. This results in blends with higher impact strength. Grade with high slip wear properties. Modification of polyoxymethylene with graphite, PTFE, and mineral fillers. These additives enhance the abrasion resistance and slip properties. Ultraviolet stabilized grades. Ultraviolet stabilizers and absorbers are often added to polyoxymethylene resins or blend to improve ultraviolet stability. For example, hindered amine light stabilizers. Nanocomposites. Additives such as CNTS, POSS, Zeno, etc. are used to produce polyoxymethylene nanocomposites. Benefits of polyoxymethylene over metals and thermoplastics. Benefits over metals. Design flexibility. while our thermoplastic it has low coefficient of friction. Our metals high strength to weight ratio, while our thermoplastic good creep resistance. Our metals it has color matching possibility, while our thermoplastic it has good toughness resistance. For metals, it inherent lubricity, lower finished part cost. It has opportunity for part consolidation and chemical corrosion resistance. While our thermoplastics, it has hard surface with good appearance. It has high strength and stiffness. It has excellent dimensional stability, as we discussed earlier, and excellent chemical resistance. Here are some typical applications of acetal design. Polyoxymethylene resins are widely used in the production of precision parts. These applications demand good dimensional stability and sliding properties. Let us enlist some of the important uses of polyoxymethylene below. First application is automotive modern fuel system. Typical POM applications in fuel systems are extremely versatile. They include components in fuel caps, fuel filler necks, fuel cylinder units, lifetime filter valves, fuel pumps, and fuel rails, among many others. Not only do these products have excellent long-term resistance to gasoline, diesel, and methanol or ethanol-based fuels, they are also able to withstand temperatures of more than 100 degrees Celsius. Next, we study the automotive interior appearances. Appearance. To meet the current trends in automotive interiors for soft, warm finishes, polyoxymethylene offers a molded in low class effect for automotive interior parts. Also, it provides a system cost benefit when compared to painted components like PCABS, and other benefits include its durable low class surface, it is resistant to cleaning solution, it has excellent dimensional stability, and it provides design flexibility. The potential applications within automotive interiors, which require low gloss, include seatbelt adjuster, cord locks, speaker grill, HVAC control panel knobs, automotive clip. Polyoxymethylene for low volatile organic compound performance. Low volatile organic compound performance are a group of organic chemicals that can evaporate into the air and may have short or long term adverse health effects. Volatile organic compounds are often found in various parts, including paints, solvent, and household cleaners. The issue of in vehicle air quality is becoming increasingly important in the automotive industry due to its direct impact on passenger safety and comfort. The reduction of volatile organic compounds significantly contribute to an improvement of the cabin air quality. Thus, both polyoxymethylene material suppliers and the part manufacturers are keeping it in mind while developing vehicle components and contributing to a better air quality in vehicle closed environment. Here are some examples of polyoxymethylene. Delrin. Delrin 300T acetyl design by DuPont. DuPont has developed an impact modified low emission grade which is suitable for use in automotive interiors. According to the company, test of samples of Delrin 300T revealed formaldehyde emission of 1.0 milligram per meter per square and lower. Medical and healthcare. Materials of construction play a central role in the design of new equipment. As the patient community demands increased safety and accuracy from providers, these dictates are ultimately met through high performance materials like powder inhaler, insulin syringe. Using polyoxymethylene in medical technology can help reduce total manufacturing cost through consolidation of multiple parts into a single unit and by implementation of automated assembly processes. Polyoxymethylene addresses the challenges of mission critical components and offers an array of leading edge materials that are excellent candidates for medical applications. Acetyl copolymers are easily processed, highly crystalline plastic, delivering high strength, stiffness, toughness, and lubricity over a broad range of temperatures and chemical environment. These polymers offer low extractable and high purity and are FDA compliant and pharma friendly, animal latex free. Industrial use. Pumping, conveying, and controlling liquids are important factors in the irrigation, plumbing, and process industries. For aqueous fluids, acetyl copolymers have an extensive history in parts such as housing, taps, and bowls and couplings. These parts are found in many fluid handling applications, including plumbing, irrigation, water softeners, beware dispensers, water filters, shower heads, sprinkles, water meters, and pumps. The acetyl copolymer materials offer good flow and moldability, and their very low moisture absorption permit dimensional stability in contact with water. Consumer goods. It has low fuel permeation to meet new CARB and EPA regulations on evaporative emissions. Small off-road engines and other type of gasoline-powered equipment have recently come under new regulations from the US EPA and California to limit the amount of evaporative emissions occurring throughout the fuel system, including the fuel tanks, caps, and hoses. Fuel tank, because of its extremely low permeability to gasoline and ethanol, along with excellent long-term chemical resistance and dimensional stability. Acetyl copolymer has been evaluated in small off-road engine fuel tanks found in lawn and garden and other gasoline-powered equipment, including recreation vehicles and marine engines to meet recently adopted CARB and US EPA regulations. Here are some reactions of polyoxymethylene. Like polymerization, depolymerization, oxidation, hydrolysis, combustion, and thermal decomposition. The polymerization of formaldehyde represents the formation of polyoxymethylene polymer, and depolymerization. Depolymerization is the reverse reaction where the polyoxymethylene breaks down into the individual formaldehyde units. Oxidation. Polyoxymethylene can undergo oxidation reactions, especially under high temperature, which led to the formation of carbonyl groups, as we can see in this reaction. When the CH2O and the POM reacts with the oxygen, it can form a carbonyl group with the release of water. Hydrolysis. In the hydrolysis reaction, we react polyoxymethylene with water, and it result in the formation of polyformic acid HCOOH. Combustion. As we know that combustion reaction always release carbon dioxide and water. When we react polyoxymethylene with oxygen, it releases carbon dioxide and water, CO2 and H2O. Thermal decomposition. At high temperatures, polyoxymethylene can undergo thermal decomposition, which, which can release carbon monoxide, carbon dioxide, and water, as we can see in this reaction. Now we discuss the global market overview of polyoxymethylene. As what is the demand of polyoxymethylene in this world? Demand for polyoxymethylene worldwide was declined by 5.2% year over year in 2020 due to the decrease in the demand from automotive and transportation and industrial applications because of the impact of coronavirus pandemic. As we have to face the lockdown during this pandemic situation, so the use which reduce the use of transportation. Global demand for polyoxymethylene recovered in 2021 and continued the momentum through 2022, and thereby registration of volume CAGR of about 1.9% during 2019 to 2022 period, attributed to firm demand from electronic appliances and medical sectors and recovery in automobile production also. The report views, analyzes, and projects the global POM market for the period 2019 to 2028 in the terms of volume in metric tons and value in US dollar and the compound annual growth rates projected from 2022 through 2028. Here are some physical properties of polyoxymethylene. like density, melting point, formula, appearance, electrical resistivity, heat capacity, magnetic susceptibility. The density of POM is 1.41 gram centimeter per centimeter cube, while its melting point is 175 degrees Celsius. And the formula we discussed earlier, its appearance is colorless solid, but it is also available in white and black color, but not in transparent color. Its electrical resistivity is about 14 into 1015 ohm centimeter, while its heat capacity is about 1500 joules per kilogram per Kelvin. Its magnetic susceptibility is minus 3.6 into 10 raised to power minus 6 at 22 degrees Celsius. Here are some references of my presentation. Thank you so much.